Okay, let's get started. I want to begin the lecture with another example to show some of the concepts that we studied last week. Essentially, applications of the first law of thermodynamics to problems such as this one. So in this example, we have, again, a cylinder with a piston. It contains water. We know the volume of the piston, the volume of the cylinder. We know how much mass there is in that cylinder. And we know the pressure. So that you should be able to know. It gives you enough properties for you to determine the state. Because from the volume and the mass, you can, of course, get the specific volume. And specific volume and pressure would be two independent intensive properties. We also know the piston is unrestrained. We have seen this before. So there is no friction between the piston and the walls of the cylinder. And the process is very simple. We're going to heat up this water until it reaches 300 degrees Celsius. And then we're asked to find the amount of work done by the system and the amount of heat transfer that has taken place. So it's fairly straightforward. As I said, we can find out the initial state. Another thing that, of course, we know by now is that this is one of those cases where the pressure is going to be constant during the process because the piston, again, is unrestrained. So if you do a force balance on the piston and assume that it is in equilibrium, you get that the pressure inside the cylinder has to be a constant. So it is a constant pressure process, which means that we could start, as I told you last time, by drawing a diagram. So if we do in this case, it might be useful since we know the initial pressure and we can find out the specific volume, then we can make a plot of pressure. Let's put that pressure in kilopascals and then specific volume in cubic meters per kilogram. And then we represent a dome there for the saturated liquid vapor region. And the first thing, of course, is to find out where we are at the beginning. And so I can find the initial specific volume, V1, by simply taking this volume and dividing it by the mass. So 0.1 over 0.5 is 2. And that's going to be cubic meters per kilogram. So that will allow me, 0.2. That will allow me to now go into the tables. And I'm hoping that by now you all can do this, but just one more time, if you go to the pressure table for water, saturated pressure table, then since the given pressure is 0.4 megapascals, which is 400 kilopascals, you would come here to the 400 kilopascal line and look at your V sub f, which is going to be about 10 to the minus 3, and look at your V sub g, which in this case is 0.46. And since our our specific volume is 0.2, we are in that range. So we know that, that we are indeed inside the dome. So we can then go ahead and put let's move this away, put a dot here for the initial state. And as I said, it's a constant pressure process, so we know we're going to have to go to the right. We're expanding. And the next question would be to determine where we end up at. And as the problem statement says, what we do know is that the temperature at the end state is 300 Celsius. This was the initial pressure, which was 400. And this was the initial specific volume, which was 0.2. So I can put all of that in there. But of course, I also know the final pressure. What is the final pressure? It's the same as P1, so it is 400. So unless I am inside the dome, we would have two independent conditions. So how do I know whether this is inside or outside the dome? One answer is experience. You know, once you've done enough problems, you can get an idea of whether a certain pressure and temperature for water is inside or outside the dome. But how else, if I don't have enough experience yet? Okay. You can go to the very same table. So if you go to the very same table that we were just looking at and take a look at one more item, and what is that other item? The saturation temperature. So we know that at 400, the saturation temperature is about 144 Celsius. So that would be the saturation temperature corresponding to this 400. So for any state inside the dome here. But since our temperature is 300, it's clear then that we're superheated. So that means that as far as the figure is concerned, we know that we have to go past the saturated line, and if this was 1, then this is 2. Okay, so the rest is fairly straightforward. We can get that quality. I don't see if it would, they didn't ask us to get that quality, but we could get it if we wanted to know the quality at 1. What we do need is that specific volume at 2, and of course I am going to get that from the superheated table using those two values. I'm going to get a V sub 2, and maybe we can do it also for this one example. So I need 400 kilopascals. So I would go into this subtable on page 785 because that has the 400 kilopascals at the top, and the temperature is 300. So I would just look at 300 and 400 kilopascals and read that volume. 0.655. So this V2 is 0.655 cubic meters per kilogram. All right. So that means that I could immediately find the work, because remember, the work will be this area. That's the work per unit mass. My V is a little bit in the middle there, my axis, but this area is the work. So I can compute that. W12 will be P, which is constant. P1 or P2, it doesn't matter what you write, is the same. And then of course V2 minus V1, that's per unit mass, so I will need the mass which was given. So I have everything here. And this number, if you work it out, should come out to be 91 kilojoules, if you plug in all the numbers. So that answers the first question. And then the second question was to find the heat transfer. And I always, in a problem like this, would find the heat transfer by using the first law. So you would write the first law in general. You could write it as delta E, which is E2 minus E1, capital, extensive total energy, is equal to Q12 minus W12. I just computed W12. Then I need to make an assumption, because this is total energy. And the common assumption is to say that you will neglect any form of energy other than internal energy. So if only internal energy is considered, only internal energy, then this equation is now delta U instead of E2 minus E1. So let's go ahead and solve for Q12. It will be delta U, so U2 minus U1 plus W12. So I already have W12. Of course, I'm not going to get any extensive properties in the table, so I have to write this as in terms of the specific internal energy. So I will write M lowercase u2 minus lowercase u1 plus W12. And again, we calculated the work. We have the mass, so we need U1 and U2. Let's start with the second one. U2, where do I get U2? Same table that I was just looking at. So go back to that superheated table, that 400 kilopascals and 300 Celsius, and read one more item there. We read the V, the V, but let's now read the U. So 28, I'm going to round it up, 2805, rounding it up. So what did I say? 2805. So 2805 kilojoules per kilogram. And then I still need U1. How do I find U1? U1 is in the dome. So what is the expression for U1? Raise your hand if you know it.
It's the same as V1.
So can you tell it? Can you give it to me? Good practice for you.
It's X UF minus 1 minus X.
Kind of close. You have it right there?
U sub F plus X U sub FG.
Right. Okay. So memorize this. You're going to use it. You should have already been using it quite a bit for any property in the dome. So whether it's a specific volume or internal energy, as we are starting to use, or enthalpy, as we will use also quite frequently, is the same combination. So, so of course I can go back and read the UF and UFG in the original table, in the saturated table. This is the first one that I showed you today. I'll let you do that on your own. Go to the table and get those values. And then that finishes the problem, because now I can plug in everything and you should check your numbers. I'll give you the answer if I have it. Maybe I don't. I don't. So let me just write, I guess I could look up the numbers and write them up, but you can do it, so get it. All right. Get the number once you plug in the UF and the UFG. So this is a very simple problem. And what I want to do is actually show you something, another way to solve this problem. And it has to do with the concept of enthalpy. And I asked Doreen to give you that concept on Friday, so I hope she did. But let's define another property and call it enthalpy. And so just think of it as a definition for now. It's a definition of another property, capital H for the extensive property enthalpy, and it's simply equal to the internal energy plus the product of pressure times volume. As I wrote it there, it's an extensive property, but if I want to write it in intensive form, that is per unit mass, all I have to do is divide by the mass. And if I divide by the mass, then I have the lowercase h, which is the specific enthalpy. Now the capital U turns into a lowercase u, and the volume turns into a lowercase volume. So either expression, depending on what you're doing, whether you're working with extensive or intensive properties, that's what you have. And as I told you, if you need to do a calculation of specific enthalpy I'm sorry, it was kind of trimmed there. In the dome, then you use the expression that we just had in the previous problem. So H equals HF plus X HFG. So we have this property, and in the problem that we just solved, we could have used this concept. But you have to be very careful if you want to use this on a problem, because what happens here is that in our problem, the pressure was constant. It was a constant pressure problem. And of course, let's write the enthalpy change in this process. So suppose that I want to calculate delta H for our problem on the previous page. Shrink this a little bit. Then, of course, this would be H2 minus H1. Right? And then if I use the definition, this is U2 plus P2 V2, and then minus U1 minus P1 V1. That so far is general. This is a general result. But let's group terms in a different way here. So let's take the U2 minus U1 and put them together here on the first part of the right-hand side. So I've taken that and that. And now the pressure. But in our problem, the pressure was constant. So P2 and P1 are the same. So I can just write P, either one. And then I have, of course, V2 minus V1. So that's the only thing that you have to be careful about, that this is only true if P1 equals P2. But then if we do that, what do we have here? This is U2 minus U1. And what's P V2 minus V1? Is the work that we just computed. So it's that. And of course, that is exactly the same thing we had. Where did I solve the problem? Right here. Is exactly this. Right? M lowercase u1 minus u2 plus w12, or if you look at the, before I wrote it in terms of specific internal energies. So it just so happens that in this problem, this happens to be Q12. So what we're getting is that in this problem, if we want to write a summary of this, is delta H. So it's a very quick way to find the heat transfer rate, but, and it's a big one, make sure that it's a constant pressure process. All right? It's for a constant pressure process. So let's put that in red so we make sure that we don't forget that. All right, does anybody have a question? You don't have a question, but anybody else? Okay, so let's move on then and talk about something else. And the something else is the concept of specific heats. And let me take a look here, see how far I'm going to go. Okay, so let's talk about specific heats. You have seen specific heats before because you've taken physical science courses. Does anybody remember the definition of a specific heat? Vaguely. Let's try to put it together with some help. Who wants to start helping? He wants to start helping. Okay.
The amount of energy it takes to burn 1 kilogram.
Amount of energy that it takes to burn 1 kilogram. Not quite. Not burning.
Isn't the energy required to raise like this by 1 degree?
Yeah, that's a lot closer. So the amount of energy required to raise the temperature of something by 1 degree. What is the something? What? No, it doesn't have to be water. Any substance. But how much of it? 1 unit. Right? So it depends on what units you're using. If your unit is kilogram, then it'll be 1 kilogram. If your unit is pound, it'll be 1 pound. But 1 unit. So, so the question that we can ask ourselves is this, based on the definition that we just gave. So suppose I ask you this question. Well, then tell me how much heat is needed to raise the temperature of 1 unit of mass by 1 degree. Right? Because that's what you're saying specific. Well, some of you are saying that's specific heat. So what's the answer to this question? How much heat do I need to raise the temperature of 1 unit of something, any substance, by 1 degree? Huh? What is the answer? It varies from substance to substance. That's very important. Suppose we fix the substance. Let's take water. People wanted to use water. So suppose it's water. The answer is that it depends on how you do it. Because there are many ways in which you can raise the temperature of a unit of mass by 1 degree. Many ways to do it. We've already seen different processes. So for example, tell me one way I can do it. Not the specifics, but what type of a process? We have a unit of water here in this container. What type of a process could I use to raise where I add heat to the substance and raise the temperature by 1 degree? For example, I could do it at constant volume. I could put the substance in a rigid tank, right? And add the heat and see, and then find out when I measure the temperature when it goes up by 1 degree, then that's what I call specific heat. So another way. So that's in a rigid tank, constant volume. From all the problems that we have looked at, which other way could we do it? In a piston cylinder arrangement, meaning that it will be constant pressure. Right? So there's 2. In fact, those 2 are the most important ones for us to consider. So we can do this, adding heat to the system in a constant volume process, or we can do it in a constant pressure process. And you will not be surprised in the end to see that the amount of heat that you need to add is different. Right? It's not the same. So let's take a look at the first one. And so let's take a look at this. See what we're doing here. So let's say we're doing it at a constant volume. So for specific heat, I'm going to use the symbol C. You've seen that before. So C means specific heat. Always remember the definition. And the subscript means how I am doing it. So I'm going to do it at constant volume, so I put a subscript V. So by the definition is the amount of heat that I will need to add. Let's call that amount of heat delta Q, because I'm only going up by 1 degree. So I go delta Q over dt, because it's per degree. If I raise the temperature by 2 degrees, I'll need about twice as much. So delta Q over dt will give me the heat per degree. And then I also said it was a unit mass, so I have to do a 1 over m divided by the mass. That will give me the C sub V. And I also put in parentheses there a V, because again, I want to make sure that I specify that I'm adding the heat at constant volume. So that's why there is another V there, not only in the label of the specific heat, but also in the process itself. Now I can write the first law of thermodynamics. And the first law of thermodynamics, if I neglect kinetic energy, potential energy, and so on, like we just saw in the problem, would tell me the change in internal energy during this process, du, is delta Q minus delta W. But it's a rigid tank. There is no work, so I'm crossing the work out. And therefore, I can see for this case that the Q happens to be equal to the du. So I'll make that substitution. So instead of Q, I just have now a du. Instead of delta Q, I have a du. And then the last thing I do is, well, since this is a capital U, but I have a mass outside, I can divide and make it a lowercase u. So I can write it as the change in internal energy per time, or expressing it mathematically, the partial derivative of u with respect to, I'm sorry, not time, temperature, capital T, and then the little v outside to denote that this is a constant volume. So it's very easy to get to this expression, which is now a formal definition of the specific heat at constant volume. So it's partial derivative of internal energy with respect to temperature at constant volume. Let's now look at the other scenario. If we repeat the experiment, but now we put it in a cylinder with a piston and see what happens, we write the same thing. All right? So now this is in the piston. I'm sorry, in the cylinder with the moving piston. I add the heat. It's nothing but the problem that we just solved, right? Except that in that problem we were driving the liquid to superheat. We just want to go by 1 degree, but it's a similar arrangement to the problem I just solved. So I write the same thing. The only difference is now I have a P for subscript because it's a constant pressure, and I have a P outside here. And again, I go back to the first law of thermodynamics, write it one more time. I make a different substitution this time. I say delta Q. I'm not going to cross out the work because now the piston is moving, but we just learned that the work is P dV because it's a constant pressure process. And as we saw, I can write that dQ as dH because we just saw that using the enthalpy. So that's the last substitution I make. Now I can, in this case, replace the delta Q with a dH, and I have that result. So I have C sub P 1 over m dH dt at constant pressure, make it specific enthalpy divided by the mass, and then you get that. So you have these two expressions, which are formal definitions of the specific heats at under these two conditions. So at constant volume and at constant pressure. And as I said, those are the two that we are going to be interested in. But let me ask you another question. In these two cases, which one do you think will need more heat? If I measure the amount of heat that I need to increase the temperature by 1 degree, and I do these two experiments, one in a rigid tank, one in a cylinder with a piston, which one will take more energy, more heat? Constant pressure? Why? Because I have to move the piston. Right? So in the rigid tank, all I'm doing is putting all the heat into the substance. Right? In the cylinder with a piston, I'm putting this energy in, but some of it is going to have to be spent in moving the piston. So therefore, in the constant pressure process, I expect the specific heat will be larger.
What if you did it with a weightless piston?
I still have an atmosphere to fight against on the other side. Right? So the only way that there would be no work, remember, as long as there is a force and a displacement, there is work, right? So if there has to be a pressure, if there is no pressure, there's nothing inside. We're doing an experiment with vacuum, right? So there has to be a pressure that pushes against something. And if we want to do it in quasi-equilibrium, which is our goal, for example, then of course the pressure has to be balanced. So there is a force, there is a displacement, there's going to be work. Okay, so how can we use this? So keep that in mind. The specific heat at constant pressure is larger than the specific heat at constant volume for that reason. Now let's see how we can use these concepts when we are solving problems in thermo. So Let's look at the three phases that we usually worry about: solid, liquid, and gas. Let's look first at solids and liquids and see if we can reach some conclusions about specific heat. Let's write our expression for enthalpy. Enthalpy is U plus PV. This is general. And now let's go ahead and I'm going to differentiate that. So I'm going to take the differential of this equation. On the left-hand side, of course, that's just dH. And on the right-hand side, I have to be careful with the second term. The first term, no problem. The differential of U is du. But the differential of PV, because it is a product, will generate two terms, right? So I'll have PdV plus VdP, right? Now you can see the difference between the type of problem that we did just now, where the pressure was constant. If the pressure is constant, of course, we wouldn't have that second term, or that third term, right? And they would be what we had, du plus PdV. But in general, if the pressure is not constant, then there'll be that other term when you're calculating dH. But now, if we're dealing with a solid or a liquid, we can make some simplifications. For example, what can I assume about a solid or a liquid? That the volume changes so little that I can neglect it. For example, if I want to get a first approximation. So let's neglect volume changes for a solid or a liquid. And there is another thing which is not obvious, but you can think about it from the fact that the specific volume, at least in the units that we're dealing with, the specific volume of a liquid or a gas is a lot smaller than the specific volume, I'm sorry, of a liquid or a solid is a lot smaller than the specific volume of a vapor. I mean, we see that all the time when we're solving problems. For example, with water, when we look at this table, the saturated table, usually for water, the V sub F is around 10 to the minus 3, right? It's about 1,000th. Whereas if we look at the V sub G, is a lot larger number. So there's that big difference. So unless the pressure happens to be huge, you will always find that the quantity VdP is a lot less than the quantity du. It would take a very large pressure variation for that not to be the case. In most problems, this will be true. So if we put these two assumptions together in our equation above, then we are neglecting dV, so that's going to knock out this term, the second term on the right-hand side. And we're also saying that the VdP term will be much smaller than du. So what we're left with is that for a liquid or a solid, the change in enthalpy is about equal to the change in internal energy. And if that is the case, what happens? If the change in enthalpy is about equal to the change in internal energy, what happens? What can we conclude about the specific heats? Somebody? Should we wake him up? There's two asleep here. No. Let them rest. What do you think? What can we conclude from what we just saw?
The specific heat, the constant volume and constant pressure would be about the same.
Would be about the same. Specific heat at constant volume and specific heat at constant pressure will be about the same, because where is our definition? The difference in the two is one is du, dt, and the other one is dH, dt. So if du and dH are the same, then this is a case where the specific heats are nearly equal. Remember, this is only an approximation. That makes sense because if it is a liquid, remember, it's not turning into vapor, and I put it in the cylinder with the piston moving, and I'm just raising the temperature by 1 degree, the liquid is not going to change in volume a lot. So there is not going to be any significant work. The only reason there is a big amount of work is if the piston happens to move a lot, which will likely to occur if we have vapor. So for the C sub P will still be larger, but the difference will be very, very small. For many problems, insignificant. So if we have that C sub P is approximately equal to C sub B, then we might as well do away with the distinction and just call it C, specific heat. For a solid or a liquid, with the assumptions that we made, is just that. Okay, now let's look at the other phase. The other phase is a little bit more interesting. So the other phase, of course, is the gas phase. So this was solids and liquids. So let's look at what happens if we have a vapor. But I'm going to make a restriction. I'm going to make it even a special type of vapor. I'm going to assume that the vapor that I'm dealing with is an ideal gas. So again, this is a simplification, just like we did some simplifications for the solid and the liquid. Let's say we have a vapor, but we assume it to be an ideal gas. And let's see what happens. Well, there is something very interesting that happens, and I'm going to show it to you perhaps by looking at some data values here. So I'm going to maybe read a couple of values here. I need to go to superheated vapor. So maybe you can use this side. All right. So this is superheated water vapor. I can make it a little larger. And this is the fourth set of pressure. So let's just look at this for the time being. So 10 kilopascals, 50, 100, and 200. Right? And let's look at the value, for example, let's pick internal energy, which is this column, right? Here, 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 or there. And I'm going to pick a temperature. So for example, let's make sure there is a temperature. All of these temperatures appear everywhere. Let's pick, say, 500. So 500 Celsius, and I'm going to read the value of U in each of the subtables, right? So 500 Celsius at 10 kilopascals, I get 3132.3. And now I do it at 50, 3131.9. Very, very close. Keep doing it at 100, 500. 3131.5, 3130.7. And you're not seeing that. This is down here. Right? 500, 3131.5, 3130.7. So you can see, let's go from the first to the last at 3132.3. Let's round it up a little bit. 3132.3, 3130.7. Very small variation. Right? Percentage-wise, pretty much negligible. So what is that telling me? Tell me what I can conclude from that reading. And if I go to any other temperature, any other value, unless the pressure happens to be too big, but if the pressure is way too big, I might run into a problem, right? Because I want to do this for an ideal gas. But as long as the pressure is not huge, so as long as you are in the permissible ideal gas regime, you will see that I just showed you. What is that telling me? What can I conclude about internal energy?
It's not affected by pressure.
Very good. It is not affected by pressure very much. Right? The effect of pressure is negligible. In fact, that is exactly true for an ideal gas. That means that if I want to find the internal energy of an ideal gas, what is the only property that I need? Temperature. And that's a nice simplification, because we know that for anything else I need two. The state postulate tells me that I need two intensive independent properties to get another property. But for an ideal gas, While it is general that internal energy would be a function of two properties, for an ideal gas, the internal energy is only a function of temperature. And I only showed you internal energy, but I could have done exactly the same thing for enthalpy. So if I go look at the same value, 500, look at the enthalpy, it's 3489, and now take it to 200, is 3487. So it only changed 2 in 3,000. 2 units in 3,000. So it's the same thing. So I can conclude then that both internal energy and enthalpy are only functions of temperature for an ideal gas. That's very nice, because if I write my definition of specific heat at constant volume, for example, which is partial U, partial T at constant volume, I can forget the fact that I need to do this at constant volume. I can just say derivative of U with respect to temperature, and then I can use that and solve for du. So du is simply Cv times dt. And of course, I can write it in capital, in extensive form, if I simply multiply times the mass. So you get this expression, which you may have seen before. It allows me to find the change in internal energy of an ideal gas by simply knowing the temperature variation, the specific heat, and of course the mass. So but it simplifies my calculation quite a bit. The same thing for enthalpy. So the rest of this page just repeats this for enthalpy. So if I do it for enthalpy, then being only a function of temperature, I can write that the specific heat at constant pressure is dH dt, and then I can write what you see there at the bottom. So it's the analogous expression. The top one here is to calculate the change in internal energy for an ideal gas. In that case, you use the C sub V, and if you want to calculate the change in enthalpy for an ideal gas, then you use the C sub P. But it's a handy way to finding the change in internal energy or enthalpy for an ideal gas. Now, I was looking at a water table. So I was not looking at an ideal gas table. I was just using the water table to show you that at least under those conditions that I was looking at, that water vapor behaves pretty much like an ideal gas because the pressures were low. But what you have in your text is actually a separate table for ideal gases. So here is one such a table. These are in Appendix A, so it's the appendix before the ones you have been using. If you go to Appendix A, it gives you several ideal gas properties of different gases. And I just took air because that's the one that we use the most. So ideal gas properties of air. And so far, what you need to worry about is the entries for internal energy and for enthalpy. Do not worry about this third column, which has to do with entropy, but that we're not going to use yet, this S sub T super zero. So, but for now, for example, if you're dealing with air and you're assuming that it is an ideal gas, then this table is very handy because if you know your temperature, you can just read across the first column or the second column will be the internal energy, and then the next one will be the enthalpy. Well, and the table goes, in this case, goes from 200 Kelvin and then continues here in the second half, and it goes all the way to 3,000 Kelvin. So it gives you, over a very wide range of temperatures, this table would give you the internal energy and the enthalpy for air, if you assume that it is an ideal gas. All right? Any questions? How are we doing on time? Okay, so now what happens between Cp and Cv for an ideal gas? Okay. We already saw that for a liquid or a solid, if you assume that the variation in specific volume is very small, they're nearly the same. But we also learned in general, always the specific heat at constant pressure is larger than the specific heat at constant volume. So what if we try to find out a relationship between the two specific heats, C sub P and C sub V, for an ideal gas? We know that C sub P is larger than C sub V, but is there an exact expression that would allow me to find, say, C sub P if I know C sub V? That's what we're after here. And it's very simple. Look at this equation. H equals U plus PV. No questions about that, right? That's the definition of enthalpy. So this is enthalpy. And then I have also said that equal to U plus RT. Why? Why can I do that?
PV equals nRT.
Because PV equals, in fact, no, PV equals RT in the way I wrote it, right? Remember, you can write the ideal gas law in many ways, depending on whether you're using density or specific volume or volume. But there is a handy way, which is if you write it this way. If you use the specific volume in the ideal gas equation, then it's the easiest one to remember because it's just PV equals RT. Now you have to remember, which R is that? Is that the universal gas constant? No. No, it's not the universal one. It is the one for that gas, which you get by, how do you get this R? Universal, let's call it RU, divided by what? Molar mass or molecular weight. We call it molecular weight, right? So that's this R. But it's a handy way of doing it. All right, so let's now do the differentiation, which we're going to need for the specific heat. So let's take this now and differentiate it. So H, of course, differentiates to dH, U differentiates to du, and RT differentiates to RdT because R is a constant for a gas. So I can write that. So what happens if I now divide by dt, by the change in temperature? I get that simply by dividing by dt. And what do I have there? What's on the left-hand side? Cp. And what's in the first term in the right-hand side? Cv. So you get this very nice and easy to remember relationship between C sub P and C sub V for an ideal gas. And it's good because it's always confirming the fact that C sub P is larger than C sub V, because you need to add R to C sub V to get C sub P. All right. Questions? No. Okay. Now, this is just this first part is just a repeat. So you probably don't need to write this down. This we already wrote. So we know that Cv is the UdT, Cp is the H. There is a typo here. This is a capital T, right? dH dt. And as we wrote before, if we solve for du or we solve for dH, we can write this. Remember, the usefulness of C sub P and C sub V is that they allow us to calculate the changes in internal energy and enthalpy. So it's just a tool to find the variation in energy or enthalpy if we know the change in temperature, because the change in temperature is easy to measure, and the specific heats, you can find them in tables. They're tabulated. So I can write that. But now, so far, we have written these expressions as du or dH. But if we actually have a process, right, that goes from some U1 to some U2, right, or some some H1 to some H2, so a real process, then what I need is not du or dH, but I need delta U or delta H. And what's the difference between, say, du and delta u? Can somebody explain the difference between du and delta u?
Delta U is just an average?
No. Delta u is in fact u2 minus u1, right? So it's not an average. And what is du?
The rate?
It's not a rate because it's not divided by time. But if this is, let's say that I plot this. So here's the, any two properties. And here is the process. Okay, so here is 1 and here is 2. And I can measure delta u because I know, say, u here and u there. But what is du?
Dependent on the path.
No, it's not. That's not an exact answer.
Like a small cross-section?
Not a cross-section, a small segment. A small segment of this process. So take a little tiny segment, right? Over that little tiny segment, there is a tiny variation in internal energy, so the internal energy changes an amount du in that little segment, whereas it changes a whole delta u from there to there. That's the difference. So how do I get delta u from du? Add all the, okay, good. Add all of the du's together, which means integrate. Right? So that's the connection between a du and a delta u. So if we use that here, then of course we can write the following. Delta u, which is u2 minus u1, is the integral of du, but du is cv dt, so I can plug that in there. And I can do the same thing for delta h. Delta H, which is the total change in enthalpy, is the integral of the little dH, and that's, of course, Cp dt. All right, so how do I finish this integration? What can I do for my next step? Now I need to go to some table that will give me Cv and Cp, for example. You raise your hand.
You can pull out CV or CP.
Okay, so can I pull it out of the integral? Can we assume that Cp and Cv are constant? Let me show you a plot. This plot has Cp, right? It's a fancy Cp because it's a molar Cp divided by the universal gas constant. So, but it's Cp. Think of this as Cp. It's just a dimensionless version of it. And temperature at the bottom. All right, so what is the answer to the question? Can we assume Cp, in this case, Cp is a constant? Huh? These are all ideal gases. This is all representative of ideal gases. So, but for what? For argon, neon, and helium. What do they have in common?
Full electron valence.
Huh?
Full valence shells.
What are they? Why are they different from the others? From, I say, H2COO2?
They're very hard to react with.
Atoms. Monoatomic. Right? These are monoatomic. Right? These are diatomic. Right? Normal oxygen, normal hydrogen. And these over here now have 3 atoms, right? Triatomic. So, it seems like the answer would be, if the gas is monoatomic, sure. If the gas is monoatomic, yes. Because it's shown by real data that the CSP doesn't change. But what if it's diatomic? What if it's air? We do a lot of problems with air. Look at the curve for air. It's is the one that starts here. You can see a little tail of it right here. So it goes like this. Can you assume that it is constant? It depends. If your problem has a very large temperature range, so your delta T is gigantic, say from 1,000 to 5,000, then you can see that the air C sub P varies quite a bit between 1,000 and 5,000. But what if your problem is air going from 300 to 500 Kelvin? If it's going from 300 to 500 Kelvin, it is somewhere here at this end of the curve, where it's almost constant. So the second part of the answer then, that you can still assume if the temperature range is not too large, then maybe you can assume that it is constant and take it out of the integral. But if it is not, like I said, if it's a large temperature gradient, then you would need to know how to integrate this, because this is now, as you can see here, the C sub P is a function of time. So you would have to do the actual integration. And there are tables that allow you to do the integration and so on. Let me see how far I want to get here. Okay, does anybody have a question about this? I want to, let's see, I don't think, I want to do this just now. I'll do that next time. So I'll do that. Let me then ask you questions, and then we will finish early. So get your clickers ready. And I'll ask you a couple of questions. Okay, so if you're ready, then let me send that in. Computer. Center screen, and come back to life. Okay, so here's the first question. There are two questions today again. The first one, remember the polytropic process? Suppose you have a polytropic process. You can look back and see what the equation for the polytropic process is. But suppose you have a polytropic process where n, the polytropic exponent, is infinite. What can you say about that process? Is it A, constant pressure? Is it B, constant volume? Is it C, constant temperature? Or none of the above? And I started the, you can submit answers. Okay, so let's go 5, 4, 3, 2, 1, 0. 221 people. Okay, what's the correct answer? Let's see what you said. Oops. No more answers. Nice Gaussian distribution almost. Eh? Okay, so the most popular answer was constant volume, followed by a tie. Hey, wait a second, I messed it up. Because I restarted the clicker. Let me see if I have it. I should have it, right? I don't know how to do it though. The graph? Oh, back. Thank you. Yes. Okay, so I'll have to delete that second one. So most of you thought it was constant volume. And then that's why you were laughing, because there was only so few responses. Okay, so that is constant volume. That is correct. Okay, why is that? Remember, polytropic process is, go back here. Dot camera. It's P V to the N equals constant, right? That's a polytropic process. So, for example, you can think an easier case is what happens if N is equal to 0. If N is equal to 0, then what process is that? That would be V to the 0 is 1, so it becomes a P equals constant. So what happens if N is infinity is a little harder to see. But you can, of course, take the nth root of this before you take the limit to n going to infinity. So if you take the nth root of this, this becomes P1 to the n V1, right? And then constant 1 to the n. This is still a constant. This is still a constant. So now when you take the limit as n goes to infinity, the one that goes to 0 is this exponent. So you get P to the 0, which is 1, V to the 1, so you get V equals constant. This is a different constant. Let's call it C2. But it's a constant volume process. All right. That was a question on the midterm last year, by the way. Yes. Whoops.
So if you're saying that PV to the power of n is constant, you're assuming that temperature is constant regardless?
I'm not saying anything about temperature.
Is it related to the PV equals nRT equation?
Only if the problem said something about this being an ideal gas, but it doesn't, right? So this is, that's a good question, because he's kind of bringing in the ideal gas law. But this polytropic expression is for anything. That is the definition of a polytropic expression is given by that. Whether it's an ideal gas, a solid or liquid, it doesn't matter. So, and the question refers, let's go back to the question, refers to anything, right? It says a polytropic process. It doesn't say that this is an ideal gas. All right? Okay, so let's do the next one. Let's close that. Okay, this is a first law question. Q12 is less than, and I'll give you less time on this one so you can think fast. So Q12 is less than 0, W12 is greater than 0. Then for this system, the change in total energy is 0, less than 0, greater than 0, or none of the above. Now, I'll give you less time because I want you to think about this in your heads more than looking at your papers. But so let's go 5, 4, 3, 2, 1, and I'm still getting answers. All right, so let's not mess it up this time. Just click the right place. Delta E is less than 0. That is correct. Why is that correct? Well, there's two ways you can think about it. One is you either remember the sign convention. If Q12 is less than 0, where is that heat going? It's going out. So the system is losing heat. And if W12 is greater than 0, who is doing the work? The system. So both cases contribute to a loss in internal energy or total energy, because heat is going out and also energy is being spent in doing work. So the total change in energy is negative. It's that there has to be a decrease in total energy. That's a direct application of the first law. Okay, any questions? All right, then I will see you on Thursday.